So in the lecture today, we will focus on the how the rest term of the horizontal curve, but we'll focus on laying out in the curve with the all the definitions we specified in the previous lecture. And also, is there any questions there? So for the quiz, it's not live. The quiz is actually assigned yesterday, but if you want, I can try to make it live, maybe at the end of this lecture or after the lecture for 1 hour again for you to work with. If you have time to work on that, or if you have any technical issues, just let me know. With that, I will go through the lecture today, and let me share my screen. So in this lecture, we'll focus on laying out in the curve, definitely that will be the horizontal curve, and also try to go through the advanced technologies to design the horizontal curve, which is called the compound method to design the curve with multiple values of the radius. There will be more details introduced in this lecture. So first, let's go to see the technology to lay out in the curve. So the basic idea is like we want, if you are provided with two straight lines, that will be the road we plan to connect, and with the you can see that one from the figure in this page. In the curve is something we designed from the before we go to the field, but we have to know how we can identify the stations or the locations along the curve. This is related to the actual practical work in the field. For example, if we know that we are given the radius of the curve, and we know that for point B, it should be laid out at the location on the curve with the angle of delta, and for the point C, it should be laid out at the point on the curve with the angle of theta, as shown in this figure. So this indicates that you are provided the radius of the curve, the two angles, delta and theta, for the point B and C, and we want to find out what's the value of where is the point B and point C. And if we are started at the point A, say that this is the start point. You stand at the point A, how can you find out the location of point B? Say if we are provided with the total station. How are you going to find out the location of point C in the curve? And that's the most critical things we need to do for the construction of the curve. And with that, we can then find out as many points as possible along the curve and connect them. That will be in the horizontal curve for two straight lines, to connect two straight lines. So to do that, you can start with the point B. Say that for the solution, we will work with the point B. For point B, we can first go to check the deflection angle between the line A to X and the line A to B. So the deflection angle indicates that the angle between the extension of A to X and also the next line A to B. So this is the deflection angle, and from our previous lecture, we can know that the angle XAB is actually just a half of delta. And we also have the formulas to calculate the length of the chord. This is the we have the closed form equation to find out the length of the A to B. That is 2 times R times sine half delta. You can go back to the previous lecture to see how this one is analyzed, derived. So with that, with these two information, you can then try to identify the location of point B. What you need to do is like you're gonna stand, or you're gonna place an total station at point A, and point at the direction of A to X, and then turn to the direction of A to B with the angle of half delta. This would be the deflection angle you're gonna do, and then you will lay out in a straight line along that direction with the distance of 2r times sine half delta. That's can anyone turn off the, okay, thank you very much. So with that, you will be able to find out the location of point B, which is the point on the curve. So that's the way for you to find out the point B. And you can also go to apply the similar method to find out the point C. So with that, we're going to consider the angle, the deflection angle, still deflection angle between AX and AC. So for the angle of XAC, it's actually half of the angle for the arc, or for the chord between A and C. So that is half of delta times theta plus theta. And of course, you can find out the quickly find out the distance from A to C. That is 2 times r times sine delta plus theta divided by 2. So you can then use the total station, apply same method to identify the location of point C. So this is one method. You can also do another method to find out the location of point C. Say that you can actually move your total station to point B, and use the extension of the line A to B, and try to find out the deflection angle between AB and BC, and calculate the chord length from B to C. The chord length of B to C it's pretty easy for you to calculate. It's 2r times sine half theta. So that's the length of B to C. And this deflection angle, say this is the Y. This deflection angle, YBC, is actually half of theta plus delta divided by 2. So this is actually the way for you to find out the location of point C from the one that I have already defined from the point B. So it's the same thing as what you it's quite similar to what you have do in point A and in point B. The only difference is like you need to calculate different lengths of the chord, different values of the deflection angles. So that's the theory we have to use for the laying out in the curve. And with that, I would like to give you a more general or standard procedure for you to laying out the curve. Assuming that you are provided with the two straight lines from, say that X to A and B to Y, and you know the starter point of the curve, that's the PC point of the curve. You know the end point, the point of the tangent, and also you can find out the intersection of these 2 points, which would be the vertex or the point of the interest. And we're gonna start to lay out a set of the points along the curve, including a letter A, letter B, letter C, letter D, and so on, depending on how long the curve is and what kind of interval you want to specify. So for the for the little point A, if we know that the angle is the angle of the arc is little d1, then we can find out the angle of VA little a as half of d1, and we can also calculate the distance of the chord distance from A to little a. That will be 2 times r times sine half of d1. So that's how you're going to find out the location of point A. And then for the next one, for next point, the letter B, say that the angle of the arc from letter A to letter B is D, capital D, which would be the standard value, the angle for the standard length, for the unity length on the arc. With that, we can find out the value of VA letter B would be D1 plus capital D divided by 2. And you can also find out the value of the chord length from A to B as 2 times R times sine D1 plus D divided by 2. So that's what they do for the little point D. You can find out location of letter B on the curve. And similarly, you can apply the same thing for the point C. So it's D1 plus 2 capital D divided by 2, and similar functions can be applied for the chord length. And the VAD, that will be D1 plus 3D divided by 2. And you can also find out the last point, which would be the deflection angle from the point A with respect to the chord length, with respect to the chord of A to B. So it's a VA capital B will be D1 plus 3D plus D2 divided by 2. Or you can apply the same equation to the length. Can anyone mute yourself? Also, if you have any questions, you can raise your hand. With that, I will be able to see whether I'll let you to unmute yourself and ask your questions. So I would like to pause here for a while for any potential questions. Anyone has any questions about the method? Okay. If we don't have any questions, I will go to an example to tell you how to complete the process of laying out the curve with the deflection angles. So assuming that this is kind of the project, the road project we want to work with. In this project, we know we want to lay out a curve from point A to point B along two different straight lines, and also we don't know how the curve is. We don't know the radius of the curve, but we are provided with some information. First, we know that at the initial line, there's a station. Say that the point C. It has the station is defined as 8800. So 8800 is in here is represent 88 plus 00. So we know the location of C as 8800. So this indicates that 8800. And we also know that this straight line C to A will tangent to the curve at point A, and but the tangent distance has not been measured. How long the distance is? It's not measured. We also have the specific requirement about the deflection and the degree of the curve, dA, which is as provided by the planner of the project, that is 38 degree. And we also, well, here dA represents the degree of the curve based on the arc definition. So you need to know what's the difference of the arc definition and the chord definition. And we also want that the station, for the full station, each full station is 100 meters. But we want to also find out the location of some substations at one-fifth of the full station length. So it means that for the substation, the interval is 1/5 of 100 meters. So that is 20 meters. That's another requirement. And also, they provide with us about the distance from the point C to the intersection. From C to V, it's 245.029 meters. And we are also provided with the angle of the whole curve, capital I, as 104°36'. So these are all the information they provide to us. And with that, they want us to find out the locations of all the four stations from point C to point B, including the station at every 100 meters and substation at every 20 meters. So this just assuming that you are constructing a road. What you need to do is like you want to place the mark on the road, and the interval of each mark would be 100 meters for the full station, and between these four stations there will be 4 marks to show the substation. We'll divide each full station interval into 5 smaller intervals with the value of 20 meters. So that's what they required. So we're going to use all this information to identify where the full station is, where the substation is along the curve. So let's go to see how we're going to try to solve this problem. First of all, we need to, we are provided with the degree of the curve based on the arc definition, but we don't know the radius of the curve. So we first need to find out what's the radius of the curve. So that's the first thing, what's the value of R. Then we should go through the definition of the degree of the curve for the arc. So we have dA divided by 100 meters equal to 360 degrees divided by 2 pi r. And this one, we know the value of dA is 38. And with that, we can find out the value of r as 360 degrees times 100 divided by 2 pi times the degree of the curve for the arc definition, 38 degrees. It will give you the result as 150.778 meters. So that's the radius of the arc, that first step. And now the next thing we need to do is like we need to know where the point A is. For now, we just know the distance from point C to the vertex, to the point of the interest, but we still need to know where the curve will start. To do that, we will need to first identify the length from A. We need to calculate the value of A to C. We need to find out the value of A to C. But generally, A to C equal to the length of V to C minus V to A. V to C is given, which is provided as let me go back to the assumption. It's provided as 245.029 meters. And we don't know the value of V2A. This is the one we have to calculate. So for V2A, we can use the angle of the arc and also the radius of the arc to do the calculation. Basically, the value will equals to r times a tangent half I. You can refer the equations that I showed in the previous lecture about the calculation from A to V. So that one give you the value of 778 times tangent. The angle of the value of I is 104 degree, 36 minutes divided by 2 will give you the distance as 195.084 meters. So that's the distance from A to V. And with that, we can find out the distance of A to C by using this equation. Clearly will give you the value as 49.945 meters. So it indicates that the point A is around 49.948 meters in the downstream beyond the point C. So we can specify the station of point A as the station of point C. The station of point C is 8800. So with that, the station of point A should be 8800 plus 49.945. That is 8849.945. We will write them in the station format. So we will put all the values in hundreds and the rest on the right side of the plus sign. So that is 88 plus 49, 945. Sorry. So that's the station of point A. Any questions about it? I guess these are yes.
Excuse me, Professor. Yeah, where did we establish the relation of VA equals R and I by 2?
VA, okay. So I'll give you a quick review about it. So now let's consider this triangle. So OA is perpendicular to the line A to V, right? Because the A is the tangent point. So this angle, the triangle AOV is in the right triangle, right? And this angle, if we refer to our previous lecture, you will know that this is just a half of I. And you know that for the right triangle, the tangent of this half I will be VA divided by OA. VA is the one we want to calculate. OA is the radius of the curve. So with that, you get the equation VA equal to R times tangent half I.
All right, great, thank you.
Good. The one important thing I would like you to remember is about the format of the station. You have to know how to write them in the right format. So on the left side of the plus sign, that will be the values about how many hundreds, how many 4 stations. Each 4 station is it's 100 meters. And on the right side, that will be the remaining distance from the previous 4 stations. So so that's the reason we have 8849. It's written as 88 plus 49. we will also use the same format for the other stations, the 4 stations and substations. Okay, so that's what we get. And now we also need to find out the location of point B. Also, or we should find out what's the station of point B. To do that, we need to calculate the we have to calculate the length of the arc from A to B. What's the length of the arc from A to B? The calculation is pretty simple. We can just use the definition of the degree of the curve to calculate length. So that is 100 times I divided by dA. I will probably start from the initial definition so that you might understand how the equation is derived. So from the definition of the degree of the curve, we have the value dA divided by 100 is 360 degree times divided by 2 pi r. And if you go to check the length of the arc from A to B divided by the angle of the arc, it will also equal to 360 degree divided by 2 pi r. So that one give you the way to calculate the length of the arc from A to B as dA times I divided by 100. We know dA is 38 degree, I is 104 degree 36 minutes, and I guess I get a put in the wrong order. That will be I divided by LAB. So with that we have the equation as 100 times I divided by dA. So it gives you the result about the length of the arc as 275.263 meters. So with that, I will just give you a quick question. What do you think the station will be? Well, I guess you have the. I'm sorry. I guess you have already see the value there in the flow and in the chart. So I'll just skip that question for you. So for the station of B, for the station B, the length along the curve should be station station A plus the distance of LAB. So at point A, the distance is 8849.945 plus the distance we estimate 275.263. It will give you the value as 9125.208. So this indicates that the station B should be 91 plus 25.208. This is what we calculate for the station B, which is also the point of the tangent for that curve. So that's the 2 locations, the 2 about the start and end of the curve we have already calculated. And now the next thing we need to do is finding out the curves in between, the locations of all the curves, all the stations and substations in the along the curve. So with our assumption, we want to find out the all the 4 stations and the substations, the minimum interval we have. The minimum interval we're gonna get is delta L is 20 meters. That's the interval for each substation. At the as we know that at the point that the station A is 8800 plus 49.945. So the next station, say that the station 1. I just say that that's the S1. S1 should be the next rounded value. So that is next rounded value at every 20 meters. 88 plus 60 meters. So that's the first station you have to lay out on the curve. This is the first one, S1, 88 plus 60 meters. And we also know that for the point B, which would be the last station, the end of the curve, that is 91 plus 25.208. And it indicates that the last station on the curve, I just assume that is SN, should be 91 plus 20 meters. So it's always running at every 20 meters. So 91 plus 20. So we need to find out all the stations in between. So so the next thing behind below the S1, S2 should be 88 plus 80, and S3 should be 89 plus 00, until you go to SN. That is what we get about 91 plus 20. We need to know what's the deflection angle we have to set, or we have to find out what's the value of D1 for the first one, what's the value of D2 for the last one, and what's the angle for each standard interval of the substations. So for the to calculate the D1, we have to know the length from A to the length of the arc from point A to the first station. Say that is LA1. What's the value of this one? This would be the arc LA1. So this one can be calculated based on the station we defined. S1 is 88 plus 60, and the station A is 88 plus 69.945. So this is 8860 minus 8849.945. It will give you the value as 10.055 meters. And with that, we can calculate the value of D1. D1 using the definitions of the using definitions of the degree of the curve. D1 divided by LA1 should be equal to DA divided by the standard length of 100. So with that, we have D1 equal to LA is 10.055 times the value of DA is 38 degree divided by 100. So that is 3 degree, 49 minutes and 16 seconds. This is what we get for the value of D1, and we can also apply the same procedure to find out the value of D2 by finding out the distance from the last station to the terminal point B. So I said that it's a LMB. So the value is 91. We're using the station of point B, 91 plus 25.208 minus the station of point N, SN. That is 91 plus 20. Gives you the value as 5.208, and you will apply the same equation. So with that, you can get the value of D2 as 5.208 times 38 degree divided by 100, which will give you the value as 18 minutes 18 minutes 45 44 seconds. That's No, that's not the way. That's not the okay. That's what we get for the value of D2. And so with that we can then calculate the value of calculate the distance of the some other values, the chord length for the first arc, the chord length here, and the chord length at the last location, at the last segment. So for the chord length, say that from the chord length from A to 1 shall be 2 times R times the sine half of D1. This is the equation we applied previously. It gives you the value around 10.054 meters. It's quite similar to the length of the arc. And we can also find out the chord length of the last segment. So this is a chord length of the MB, and this is the chord length of A1. So still we're gonna apply the same formula. D2 divided by 2 gives you the value of 5.207 meters. It's also quite similar to the arc length. So that's what we get about the chord length of the initial segment of the initial arc and the last arc. You can also try to find out the chord length of the other segments between the substations along the curve. With all those informations, we can then summarize our findings for the deflection angle, for the chord length, and laying out the locations of those substations and stations along the curve. So for the chord length of all the substations, I just say that this is CS. So for the CS, it's actually determined by the chord length of 20 meters. Not the chord length, by the arc length of the 20 meters. So this is the arc length. And we can then apply the same method to do it, to find out the chord length. So we have CS divided by delta L should equal to dA divided by 100. So with that, we have CS equal to no, it's sorry, this is a capital D. Capital D is it's the angle of the arc. So we first need to find out the capital D. So for the capital D, the value is 7 degree 36 minutes, and then we can find out the chord length as 2 times R times the sine half D, which will give you the value as 19.985 meters. And with that, you will be able to find out the all the angles with respect to each interval, including the start and end intervals, and then you can lay out the stations. So for the in this table, we'll summarize what we have already found. So for the initial station, that will be the point A, the point of the curve. We have calculated the station as 88 plus 49.4. 945, and then you have the station of 89 plus 60, 88 plus 60, 88 plus 80, and to 89 plus 0, 89 plus 20, and until you go to the last one, 91 plus 20, and then go to the point B, 91 plus 25. and you'll be able to find out the chord length for the first segment 10.054, and the chord length for the last segment 9.207, and also you can find out the chord length for any intervals between the substations, and you can use the value of the value of D1, and also apply with the this is just a half of D1 to find out the deflection angle, and for the second one that will be D1 plus D divided by 2. The third one would be D1 plus D2D divided by 2, and you can continue to calculate the deflection angle until you reach to the last one for the deflection angle from A to B. So that's how you're going to lay out the curve, by finding out the chord length, finding out the deflection angle. With that, you will be able to find out the exact location of any points or any stations you specified along the curve. So that's the first method we applied to laying out in the curve with the deflection angle. And the second method, we also can apply another method by utilizing the total station system. So with that, you don't need to go to any substations along the curve. Instead, you will only place your total station at point A, and then try to calculate the chord length from A to all the stations. In this example, from A to station 90, 91, 95, 93, and you go to the 98 and point B. Then you can calculate find out the deflection angle with respect to each station. For example, for 96, you just need to find out the deflection from A to V and A to the station 96. And once you have the deflection angle, say that is usually that will be the half of the angle of the half of the angle for the arc, and you can also find out the chord length based on the formula we provide. L equal to 2 times R times sine the half of the sine the deflection angle. And so that's the way for us to use the total station. We don't move the total station, we're just changing the chord length and also the deflection angle to laying out in the curve, the stations along the curve. And we also have another way to apply the total station. Say that you don't know which you don't know any point about the curve, and your total station is not set at the along the straight line or along the curve. Instead, you put the total station at any random point that is outside of the curve or the straight line, and then you're going to calculate the angle from the station to the control point with respect to the reference point. Or so we define this one as the reference point, or reference line, sorry. So we find out the angle with respect to the reference line, say is theta, and then we calculated the offset from the control point to the station. And say that this length is L1, then you can use the angle and also the distance you estimated for the calculation for laying out in the curve the stations along the curve. So this one will involve with some more calculations, especially about the relative locations from the control point to the stations. So usually we're going to use the coordination method. to find out the locations of the station and their relative directions and the distance to from the control point to the station. Or it's just an alternative method that you can apply. So I think I don't have time to go through the next topic about the compound curve. This is another method which we can use to design more complicated horizontal curve with different radius. With that, you will have different curvatures along the same curve. I will go through the details about the calculation in the next lecture. So with that, I will stop the lecture here. And do you have any questions for now? If I will also, in the meanwhile, I will also try to make the quiz alive for you for another hour, and you can then try to work on the quiz for the second time. This is the same quiz I assigned yesterday. So if you have any questions, any technical issues, just let me know. You should be able to see the quiz for now. Okay. Okay. Do you have any questions about lecture today? If you have any questions, can raise your hand or just leave your message in the meeting chat. Okay, if we don't have any questions, I guess that will be all for the lecture today. And just feel free to send me email. Or there are questions about the quiz. The quiz is on Avenue, and as usual, this time I just make it offline, not in the class. So you can work on that. Okay. Okay. If there's any additional questions, I will close the meeting today, and I really appreciate your attendance. Just feel free to send me email or email the TA if you have any questions about the homework assignment, about the course notes, and so on. Okay, great. Thank you very much, and I will see you next week.